Okay, so in this video, we're going to talk about the timing of the carbon cycle. We're going to split it up into two cycles again, but this time the fast carbon cycle and the slow carbon cycle. So in this video, we'll start by comparing the sizes of key carbon reservoirs, and we'll define this new term of steady state, contrast that with the concept of equilibrium that we brought up in the last video. We'll also calculate the residence times of different carbon reservoirs, or how long the average carbon atom will spend in these different reservoirs of the carbon cycle. And then once we have this estimate of a time scale, we'll differentiate between the short and long-term carbon cycles. So this is a bit of a review from the last video, but there's several key places where carbon resides on Earth. The first is CO2 in the atmosphere. This inorganic carbon is fixed into biomass by land plants, which then finds its way into soils. Carbon from the atmosphere can also dissolve into ocean water, and here it can be fixed by phytoplankton into biomass, or it can be mixed into the deep ocean. Both inorganic and organic carbon can wind up in ocean sediments and can either be turned into sedimentary rocks or seducted into the mantle. So now let's compare the sizes of these different reservoirs. And the unit that we'll be working in common is the gigaton. So 1 gigaton, or GT, is 1 billion tons. And 1 ton, in the metric sense, is 1,000 kilograms. A kilogram, remember, is 1,000 grams. So sometimes if you're reading up on climate change or the carbon cycle, you'll see this word petagram instead. Petagram is the exponent of 10 to the 15, but it's exactly equal to 1 gigaton. So the atmosphere today has around 600 gigatons of carbon dioxide in it, but this is actually one of the smaller reservoirs of carbon on Earth. Contrast this, for example, with the amount of carbon in the mantle, which is over 100 million gigatons. Sedimentary rocks have around 60 million gigatons, whereas the deep ocean is the next largest reservoir at 37,000 gigatons. There's also a significant amount of carbon in marine sediments. Compared to this, the other reservoirs are relatively small. Soil carbon has around 2,300 gigatons, land plants around 550, and the smallest one here is the marine biosphere. It's around 3 gigatons. Now there's an almost infinite way to keep parsing these different groups, but these are the main players in the carbon cycle. So for the most part, the sizes of these reservoirs are known pretty well. And so the big uncertainty in a lot of climate change research is really the exchange of carbon between atmosphere and land plants, between atmosphere, soil carbon, between atmosphere and ocean. The magnitude of these fluxes and how sensitive they are to environmental changes are really what most researchers are trying to find today. Even though material is constantly exchanging between these different reservoirs, their sizes are relatively steady. We can understand this phenomenon by defining a steady state. So a steady state develops when the input and output fluxes to a given reservoir are balanced. So we can imagine this pretty easily as a tank of water with a faucet that's adding water to the tank, and then another faucet that's allowing water to drain. If you've seen anything like this in real life, you have this intuitive sense that the height of this water column will influence how fast water will be forced out this sink. And so in some ways, the removal of water, in this case, from this tank is dependent on how much total water is here and how much pressure is pushing down. The other thing this cartoon illustrates really nicely is that even though there's constantly water coming in and constantly water leaving, you can arrive at a relatively steady height of this water. And this is really a perfect illustration of a steady state. There's this constant turnover of water in the tank, but the size of the reservoir is the same. Now, there's two key things to keep in mind with this. The first is that multiple steady states can be possible with given input or output fluxes. The second is that this is entirely different from the concept of chemical equilibrium we discussed, talking about the forms of carbon that dissolve in water. And really, to arrive at a chemical equilibrium, you need a system that's mostly at rest with very little inputs or outputs. So it's really just atoms interchanging back and forth. And so in a sense, equilibrium can be imagined as a tank without a drain and without a source. Eventually, the chemistry of this water will come to rest. The volume of this water will come to rest and stop changing. But we can also illustrate cases where two different steady states might develop. So for instance, in this state one, we have a pretty small input of water. This faucet here is just trickling in water. And as a result, the height of this tank is pretty low. because the height of this tank is pretty low, the water that's leaving the tank isn't being forced out. It's also just trickling out. And so you can arrive at a steady level of water in this tank with a relatively weak flux of water into it. Now we can also imagine this more vigorous case where you have a stronger input of water from this top faucet, and that allows more accumulation of water in this reservoir. You still have water leaving this tank, but the size of this total reservoir, again, is steady, but it's expanded. So these are two alternate steady states. And this is important for considering the magnitudes of different pools of carbon on Earth's surface. The total amount of gigatons in the atmosphere, for instance, is really just the combination of input fluxes into the atmosphere and removal fluxes out of the atmosphere. And so any steadiness of carbon dioxide in the atmosphere over periods of hundreds to thousands of years is really reflecting these steady states that we were illustrating with water before. So to look at this exchange, let's consider the rapid carbon cycle, or the carbon cycle of Earth's surface. And so here we've cut out sedimentary rocks and the mantle, and we're just considering the ocean, the atmosphere, and the land biosphere. Through a lot of efforts over several decades, we have estimates of the global fluxes of carbon from the atmosphere into plants via photosynthesis. This is around 120 gigatons per year. And the respiration of land plants, they need to build biomass, to build new leaves every year, that's around 60 gigatons. And then there's also this flux of carbon from land plants into the soils due to things like leaves falling from trees or trees falling and being decomposed into soil. And the consumption of that carbon in soils releases carbon back to the atmosphere. Each of these fluxes are estimated to be around 60 gigatons per year. They're of a similar magnitude. So now that we have these fluxes illustrated, we can ask a pretty simple question, which is how old is the average forest or the average ecosystem on land? So we know that there's 120 gigatons of carbon being fixed into plants per year, and there's also 120 leaving it. So how fast does this pool turn over? So this is often described as a residence time, or how long an individual carbon molecule will reside in a plant cell before it moves on to another reservoir. And so we can start with a more intuitive analogy. So for instance, if you're flying on a plane from LAX to Hawaii, that distance overall is around 2,500 miles. If the plane is going around 500 miles an hour, how long will the flight take? You can reframe this relatively simple question into the same perspective as we had before. This distance is an inventory of how much distance needs to be traveled. And this is essentially the input flux of how many miles are you getting per unit time. So to get flight time, you would take total distance divided by average speed, and you'd come up with something like 5 hours. For calculating a residence time, it's almost the exact same thing. We take the reservoir size of the plant biosphere, around 550 gigatons, and divide it by the total inputs, or 120 gigatons per year. So 550 divided by 120 equals 4.6 years. And so to be honest, this is a bit incredible, right? I mean, you often think about trees that are around for decades, if not centuries, if not millennia even. But on the other end of the scale are leaves from these trees that may only be around for a spring and a summer and then fall to the earth during autumn. At the same time, there are grasses that grow and die every year. And so the average over the entire Earth's surface is only around 5 years or so. That most of the carbon in Earth's plants is turning over relatively fast. Notice also you get the same solution if instead of using the inputs, you do this calculation with the outputs. If you did that, you would have 550 divided by 60 into soils and 60 back to the atmosphere, and you would have the same 4.6 years. The same result is a definition of steady state. The input sources match the outgoing fluxes. If these fluxes balance, the size of this reservoir doesn't change, even though all this plant carbon is turning over every 5 years. Now that we've characterized this terrestrial carbon cycle, we can extend this to the oceans. And so estimates for exchange of carbon between the atmosphere and the upper ocean are on the order of 90 gigatons of carbon per year. And so we can ask a similar questions, like what's the residence time of carbon in the atmosphere? How fast does atmospheric carbon dioxide turn over between the oceans and these land-based reservoirs? And this calculation is very similar to the last one. So on the top, in this numerator, we have the reservoir size, 600 gigatons in the atmosphere. And in the bottom, we have the total inputs. So we have one input from soils at 60 gigatons. We have one input due to plant respiration at 60 gigatons. And we have one input from gas exchange with the ocean at 90 gigatons. So it's 600 over 60 plus 90, which comes to around 2.9 years, or 3 years. And so when I first saw this kind of blew my mind. I mean, you sort of think about the sky and you kind of imagine that the sky you're looking at is always kind of the same. But based on this calculation, all the carbon dioxide in the atmosphere is cycling through these land reservoirs, these ocean reservoirs pretty quickly. So every 3 years of your life, you have a totally new atmosphere of carbon dioxide, which I think is crazy. Okay, here are all the fluxes of this rapid carbon cycle sketched out. So we've discussed the land cycle, we've discussed gas exchange between the ocean and the atmosphere. The upper ocean will exchange carbon with the deep ocean. This ocean is sort of defined as the part that isn't connected to the atmosphere every year. And the magnitudes of this flux is really dependent on ocean circulation. Like how fast is the ocean actually mixing? And in the middle of this, we have this marine biosphere that's fixing carbon from the upper ocean where there's sunlight and mostly being grazed and returned back. And there's this small bit that ends up sinking into the deep ocean. And we'll talk about this more in the next video. It turns out to be super important to Earth's climate. But as we've done for the plant reservoir and the atmosphere reservoir, we can calculate residence times of all of these different components of the carbon cycle. So here's our 3-year estimate for the atmosphere, 5 years for land plants. It's interesting to compare land plants, which are around for several years on average, versus the marine biosphere, which is only around for 15 days. And this makes sense too. I mean, you can walk through a forest and see, tons of plants around, but in the ocean, usually you have to filter liters and liters of seawater to even see a bit of green. Now, the upper ocean, in part because it's connected to the atmosphere and is also exchanging carbon much more with the marine biosphere, has a pretty short residence time too. So the carbon, the surface of seawater that you would see as you look out over the ocean, that carbon is turning over every 4 years or so. But in contrast, the deep ocean, the only real exchange of carbon in the deep ocean is with the surface ocean due to this long time scale of ocean circulation. So the estimated residence time here is over 400 years. And so you can think about carbon in the deep ocean as being a much longer term storage than carbon in soils, which turn over on average of 35 years or so. This has a lot of implications for thinking about where fossil fuel carbon is released to the atmosphere, where that will end up, and how fast and how long can it stay there before it's returned to the atmosphere. But that's this fast carbon cycle. But there are other really important processes that add carbon to this cycle and also remove it. So to consider the slower carbon cycle, we'll add up all these reservoirs together. In total, there are around 41,000 gigatons. And you can see here the dominance of the deep ocean here. This is over 90% of deep ocean carbon in this total sum. So the ocean is really controlling how much carbon there is in this rapid carbon cycle. And now we can compare these sort of geologic reservoirs of carbon. You can imagine that the total amount of carbon that's split between the ocean, the atmosphere, and the terrestrial biosphere really depends on the exchange of carbon between the rapid carbon cycle and these geologic reservoirs. So here are best estimates for the exchange of carbon between these different reservoirs. There's around 0.5 gigatons of carbon that leaves the oceans every year and is stored in marine sediments. A lot of this will return back to the ocean. At the same time, the carbon in marine sediments will eventually either be subducted into the mantle or be uplifted back onto the land in sedimentary rocks. And these can be weathered and washed into the ocean through rivers again. So this is a return mechanism for some of the carbon that's been sequestered for long time scales. So the major new input of carbon into this rapid carbon cycle, as we discussed last time, is due to volcanic activity. This is estimated to be around 0.03 gigatons per year on average. But really that average swings a lot. In some years, there's almost no volcanic activity. In other years, there's massive eruptions that are 10 times this value or 100 times this value. And so this is something that can really change quite a lot over different timescales. So we can calculate a residence time for this rapid carbon cycle as a whole, and it's around 77,000 years. We can differentiate the rapid cycling of carbon in those pools versus this super slow exchange between these geologic reservoirs that are actually much, much larger. So even though there's tons of carbon in the mantle, the fact that these fluxes overall are really small means that under most circumstances, it has a pretty small effect on the carbon cycle as a whole. Similarly, we can calculate the residence times of these other reservoirs. So marine sediments will turn over on average every 12,000 years or so. So it's a similar time scale to the rapid carbon cycle. But we can compare that to residence time estimates of greater than 3 billion years in Earth's mantle. Similarly, sedimentary rocks on land These are part of a cycle that's several 100 million years. So the uplift of marine sediments onto land, their erosion, this is all part of a cycle that takes a long time to complete. But considering the 4 billion years history of Earth, will overturn several times, which I think is still kind of mind-blowing. At the same time, this sort of emphasizes how slowly these fossil fuel reservoirs accumulate. These are really generated from organic carbon in marine sediments that get slowly heated to the point where they turn either to natural gas or sort of liquid oils like that found in petroleum. And these will sort of accumulate in different reservoirs where they're essentially capped by other rocks. But their production seems like it's not steady over long time scales. And there's certain periods in Earth's history, most of which over 100 million years ago, that seem really critical to forming the fossil fuel reservoirs that we're currently extracting today. So most estimates suggest that since the start of the Industrial Revolution, around 25% of these fossil fuel reservoirs have already been added back to this rapid carbon cycle at a rate of roughly 8 gigatons per year now. One thing this emphasizes is that in some ways it takes 100 million years to form these fossil fuel reservoirs, but our current rate of extracting them suggests that they'll be depleted within 200 years. And so this sort of emphasizes how unsustainable this source is. We can also trace the addition of this fossil fuel carbon, this 8 gigatons per year, into the atmosphere and into the rapid carbon cycle in this period since the Industrial Revolution of the mid-1800s, the Anthropocene. So over this time, we've added around 200 gigatons of carbon to the atmosphere, and it would be higher if not for this rapid exchange. One thing that's pretty interesting about this is it seems that land plants and soils don't have a ton of excess capacity. So even though atmospheric CO2 has gone up so much, the size of these reservoirs hasn't increased very much at all. So the major work of removing carbon from the atmosphere has relied on the ocean, which has absorbed around 50 gigatons in this surface reservoir and around 100 gigatons in this deeper reservoir. And as we continue to burn fossil fuels, we'll be increasingly reliant on the ocean to keep absorbing this carbon in order to stop really high atmospheric CO2, which will lead to really large greenhouse effects. One thing to keep in mind is that while we have a sense of what these fluxes are on average under normal climate conditions, changes to ocean circulation, changes to temperature might change all of these fluxes. And so again, that's a big part of where carbon cycle research is going is to estimate the sensitivity of these fluxes. But just because the ocean has absorbed this amount of carbon so far, it doesn't necessarily mean that we can rely on it to keep doing so in the future, especially if this exchange between the upper ocean and deep ocean becomes less efficient due to enhanced warming and stratification. Okay, so in this video, we've compared the sizes of different carbon reservoirs. We've contrasted systems at chemical equilibrium, aka at rest, versus this steady state where the size of a given reservoir is constant, but the material in that reservoir is constantly being replaced by new material. And with this steady state idea in mind, we've calculated residence times of different carbon reservoirs. And we differentiated between the relatively fast overturning of carbon in the atmosphere, in the upper oceans, in the terrestrial biosphere, versus these intermediate storage of carbon in the deep ocean, versus the long-term storage of carbon in marine sediments and sedimentary rocks. With these timescales in mind, we know that all the CO2 released due to fossil fuel combustion over the next few hundred years will be relatively restricted to this rapid carbon cycle and only weakly connected to this geologic reservoirs where it's really capable of being stored for long periods of time and not interact with the atmosphere.